Thanks so much for the invitation and introduction. This is the first time making it to the seminar in real time, but I've really appreciated all of the YouTube videos from this and other seminars like Vantage. Lots of great talks. Also, my slides are available at my website. If you just Google DZB Math, you'll find me, and they're at the top. So if I go too fast, or you can follow along. Great. So this is joint work with Jeremy Rouse and Drew Sutherland, and then John Voight swept in at the end and helped us with an appendix that I'll explain later. Quick background. If you have an elliptic curve over a field, like a number field, then its geometric torsion and characteristic 0 is free of rank 2. Its torsion over K itself is generally not. In particular, those torsion points have an action of the Galois group. Literally just move the coordinates of the torsion points around. And this gives you a collection of very important representations. So the top one, the mod n, acts just on the n torsion. It's a continuous homomorphism from the absolute Galois group to GL2. As n divides m, these are compatible. So you can take inverse limits, you get the l-adic one, or you can take the full profinite limit of all of these, and you get a representation targeting GL2 z hat, again, characteristic 0. And let's talk about these. So Serre's open image theorem is a concise way to phrase a lot of things, but it says that if you have an elliptic curve over a number field without complex multiplication, then the image of this ell-adic, so the full profinite limit, the image of this is open. In particular, this is compact, so it's finite index. It's not open for non-CM. And I'll note that by the Chinese remainder theorem, or although you need some extra work to get this topologically, it breaks up as the product of the individual l-adic representations. So saying that this is open, for example, tells you that it's the l-adic ones are surjective for all but finitely many n. Or flipping back, it tells you that the index of this top one is uniformly bounded independent of lowercase n. So the goal of this talk is to understand the possibilities for these images of Galois representations. I will say there's an incredible paper by Alvaro Lozano Robledo handling the CM case. I think it's 50 or 60 pages, and a lot of other related work preceding that. In the CM case, there are less CM elliptic curves. You can ask for more, and so you can get stronger theorems. Anyway, here's the setup. So some Galois theory. First, if we're looking at the mod n or any of the representations, we'll denote by h parentheses n the image of this. So when I identified this with GL2, I picked a basis. You can talk about image inside of aught of E of n, and then different bases conjugate the group h of n within GL2. So this is only up, everything I say in the talk is only up to GL2 conjugacy. And the goal is to understand this image. So a really concrete way to think about this when K is Q, or in any K, I guess, you go from Q to Q bar. The kernel of this homomorphism acts trivially on the n torsion, right? The kernel by definition are the things which act trivially. And so if I take the fixed field of the kernel by infinite Galois theory, the Galois group of that fixed field is the image, right? Kernel group image. And then that fixed field is equal to the field you get by adjoining the coordinates of the n torsion points of E to the rational numbers. So the points are x, y. You literally adjoin x comma y. These are defined over some extension. That extension is finite. It has Galois group Hn. So if you don't like representations and just like to think about torsion fields, you can describe the problem as what are the possibilities for the Galois groups of these torsion fields? It's helpful to go back and forth, but fairly concrete. So generically, this is surjective. This Galois group is always a subgroup of GL2. It's often equal, but often not. And then this has been coined Mazur's program B for the following reasons. So everybody knows Mazur's, Eisenstein, and Isogony's papers, but he has this excellent survey paper from around the same time in one of the modular functions books, pre-LaTeX. And theorem one was uniformity. This is program B. There's no program C, just a conjecture C, which was a different version of uniformity. And he laid out this program of very generally pick a subgroup, presumably open, of GL2Z hat and find all elliptic curves whose image of Galois lands in this subgroup H. So if H is the full group, it's everything. And I'll go through some examples of why this is interesting and generalizes problems we care about. As stated, for a general number field K, this is too difficult. We don't even know possibilities for isogenies over general K, or torsion for that matter. Even for K is Q, though, this is main area of research. So main motivating example, if the elliptic curve has a rational torsion point, P, you can extend it to a basis Q, or P comma Q. So P is your first basis element. If it's K rational, the Galois group acts trivially on it, like on this almost bottom line. And then Q, the Galois group just sends it to some multiples of the basis, AP plus BQ. A and B go here and here. And so if you have a K rational torsion point, using P as part of your basis exhibits the image of Galois H as a subgroup of the group 1 star 0 star. Conversely, if H is a subgroup of that, or rather conjugate to a subgroup of that, then the first basis element helping you conjugate it into that subgroup is a rational torsion point. So first image of Galois problem, rational torsion if and only if image is contained in this much smaller subgroup than GL2. Also, a lot of older references, including my original paper with Jeremy, confuse a group with its transpose. You can kind of see why that might happen. But that doesn't cause any serious errors in papers that I know of. Many maximal subgroups, or important ones like this one, are conjugate to their transpose, or in this case, equal. So similarly, if you have a cyclic isogeny kernel generated by a point P, P is not necessarily rational, but the kernel is K rational. So every point of the kernel is sent to some multiple. And then if you extend that to a basis Q, it's sent to whatever. So you get A, B, C, star, star, 0 star. So having a cyclic isogeny is the same as image being contained in the Borel. So Mazur's two classic theorems can be rephrased as an image of Galois problem. The other maximal subgroups sometimes have a nice description. So here's a normalizer of a split Cartan. On the left, that's split torus. On the right, you normalize it. This is maximal. Technically, you can fit a moduli interpretation onto this. You can say if the image is contained in this group, but not contained in the normalizer, sorry, in the Cartan, and then you have an unordered pair of cyclic isogenies, their kernels intersect trivially. Neither is exactly K rational because of the second element, but they're quadratic conjugate. Not as clean as torsion, but it's there. And there are lots of other interesting subgroups. Another maximal is a non-split Cartan. The cleanest way is FP squared is a two-dimensional FP vector space. So letting the units of this act gives you a map like this, index 2 in its normalizer. I thought for a long time this didn't have a helpful moduli interpretation, but there is actually one from 6 or 7 years ago in terms of necklaces of isogenies. So said earlier, slide again, understand the image. It's a Galois group of the torsion field. Quite a concrete object. Also, a concrete object is the main tool that we use in our paper, not the only, but the main one, to study these modular curves. So the classical modular curves, x1, x... Oh, oops, sorry. Okay, the classical modular curves, x1, x0, parameterized torsion or isogenies, the largest index, 1, x of n, this parameterizes an elliptic curve and a pair of torsion points, so a basis for the torsion. In terms of image of Galois, if both torsion points are rational, that's the same as that Galois group being the trivial group. So in terms of group theory, it's kind of the highest index possibility. And you can cook up in several ways a modular curve x sub h that works as follows. So if I have an open subgroup of GL2Z hat, I'll define its level to be whichever minimal n, or the minimal n for which gamma of n is a subgroup of H. So it's kind of H is determined by some finite subgroup and then taking its preimage. And we can define the modular curve x sub h to be the quotient of x of n by h of n. And roughly, this parameterizes what you think it does. There are some stacky issues that are actually quite annoying. It's worse in higher dimensions. But they roughly parameterize elliptic curves whose image of Galois is conjugate to a subgroup of H. Now, I say roughly because the modular curve x of 1, I'm going to flip back, the modular curve parameterizes a choice of torsion point. Whether I use P or 2P, H is still, let's assume n is odd, H is still a subgroup of the same group. So when we talk about level structure for torsion, we mean actually keep track of the torsion point, distinguish P and a valid multiple. Here there's level structure as well. So you pick a basis, but you ask that the Galois group act on that basis by an element of H. So anyway, these are, without too many more technicalities, these are just as useful as the classical modular curves with some caveats. So Mazur's program B is really find every rational point on every symmetric power of every modular curve, including these x sub h's. That's really what we want. We'll stick to Q. Sometimes these are rational, or sometimes they're elliptic curves with rank greater than 0. Jeremy noted that there's a modular curve that is a rational point on itself. Some of these have exceptional points, by which I mean non-cuspidal, non-CM. And then you can compute the genus group theoretically via Riemann-Hurwitz. You can compute the gonality, that's the gamma, spectrally. There's a lower bound. It's difficult to compute it precisely in general, but these both go to infinity as the index goes to infinity. There's only finitely many rational up to twist. And here we go. So you saw maximal subgroups before, but we're really looking not just mod L, but l-adically. And I can give you generators and relations for groups, but I really think stacking the groups on top of each other like this, and I'll explain what I mean, is much more enlightening. So here's an example subgroup from Serre. It's a subgroup of GL2Z hat. I just call it H. If I write H of 2, I mean reduce it mod 2. H of 4, reduce it mod 4. And you get a big tower of commuting maps. So if I reduce it mod 4 and then mod 2, that commutes with taking the reduction mod 4 and mapping it to H4 to H2. And then the kernel of this map phi1 is contained in the kernel of this reduction map, which looks like the group on the left. Right? It looks like a p-adic Lie algebra. Literally the matrices which map to the identity look like identity plus twice something. Okay, but as a multiplicative group, this is isomorphic to F2 to the fourth, the additive group. If you multiply two of these, the second order terms cancel. And so one good way to think about these groups is, well, think about it mod 2. Okay, here's a group which is everything mod 2. Actually, it's everything mod 4. And then it's index 2 mod 8. And then if you go up to 16 or higher, it's just index 4 all the way up. So the group H is the preimage of its mod 8 reduction. Its level is 8, and it's or 16, I guess, and it's determined by this reduction. Okay. In general, the dimensions of these Lie algebras tell me personally, a lot more about what the group looks like than the actual generators and relations. And then sometimes you have a nice other description of the group. So a general group just kind of looks like a big mess like this. There's a group that came up in my first paper with Jeremy, where which we had to consider, where it's everything mod 2, you're missing a little bit mod 4, and it keeps getting worse. You're missing its index 4 mod 8, and then its index, well, actually 8 mod 8, 16 mod 4, but then it stabilizes. And all of these groups eventually stabilize because they're finite index. And then it's unlikely that giving you generators and relations for this group would tell you more than this picture. This is kind of what they look like. The non-prime power case is pretty interesting too. So there's an interesting subgroup of GL2 Z mod 6Z. So there's a surjection from GL2 Z mod 3Z to Z mod 2Z. Okay, either these are both power of 2, power of 3. It's hard not to have a surjection in that case, or it acts on the 3 2-CLO subgroups. That's the action here. In any case, whatever that surjection is, I can break up Z mod 6 as Z2 cross Z3. So there's a subgroup of H6 of this. And so there's a modular curve parameterizing elliptic curves whose image of Galois is contained in this weird kind of small subgroup. Brow and Jones worked out equations for the modular curve. So the modular curve is a P1, easy equations, but it has a J map. So really they worked out equations for the map to the J line here on the bottom. And then the moduli interpretation is if the image of Galois is contained in this weird group, then actually the 2 torsion fields contained inside the 3 torsion field. That's a really weird property for elliptic curves to have, that when you adjoin to Q, okay, the coordinates of the 3 torsion points, you accidentally pick up all of the 2 torsion points. Generally, these fields are linearly disjoint. So this is the opposite of that. And in fact, because this modular curve is P1, there's infinitely many. And you can quickly test whether this is true. So if the J invariant is of the form, well, here it is, this polynomial sextic T. So it's an if and only if. It's contained in here if and only if J is of this form. And then, of course, over some extension, you have both the 2 and 3 torsion. That matches up with, over some extension, you can solve this equation. At worst, an S6 extension. Anyway, we're mainly sticking to the prime power case because that's all we could do. We're working on the composite. And the conjecture of Serre is that for an elliptic curve over Q without complex multiplication, the mod L images are eventually surjective. So for L at least 37. And then actually the l-adic ones are surjective as well. And our version of this is don't just look mod L or l-adically, ask when are the representation, when is the image everything, what are the representations surjective, and what are all the possibilities? So it follows from the fact that the genus of these modular curves go to infinity that actually there's some absolute constant. I mean, assuming Serre's conjecture, there's some absolute constant such that every elliptic curve without CM has image of index bounded by this constant. And I would like to know what that constant is. So that's the goal. Start chipping away at this. There are some conjectures for what this constant is that are probably, I'm now convinced that they're probably correct. So we need notation to talk about these groups. Drew and Jeremy and Drew really helped us come up with a good labeling system, which was level index genus that distinguishes a lot of groups, and then a tiebreaker, which I won't say in detail what the tiebreaker is. We do need to use it frequently, but so the Borel has level 13, index 14. This is star star 0 star, genus 0, and then whatever the tiebreaker is, it's 1. So these give us a good way to talk about these, and if the hyperlink works, nope. These are on the LMFDB. You can download them into Magma. There's a lot there. So I gave this talk at Simon's a couple years ago and showed the obligatory XKCD cartoon. There's also the Cummings Polly Cummings labels, others, and learned at the talk, or maybe day before my talk, that Drew and the LMFD people had changed the labels slightly. For our paper and for this talk, I'll stick to the labels we have. So our main theorem is a conjectural classification of the exceptional points on the l-adic level modular curves. So if you have a point on a modular curve, it's exceptional if it is not CM or a cusp, so there are lots of CM points, and if that modular curve only has finitely many points. For example, there are infinitely many elliptic curves with rational two torsion. Having rational two torsion does not make a curve exceptional. So we'll go through that. So the theorem is pick a prime, non-CM elliptic curve, look at the l-adic image of Galois, and then one of the following is true. So we have a list from prior work of Sutherland and Zureick of exactly which such modular curves have infinitely many points. And you can see that in a table. Okay, or we have a large collection, we'll show you this in a second, of rational exceptional points, is more than you might guess. Or the group H is one of the, I'll call them unsolved mysteries in a second. There's 6, and then the ones coming from Serre's conjecture. And let me explain that. So conjecturally, for large L, actually, we know what happens for L at least 13. The non-split Cartan, that subgroup earlier, the remaining one, has no exceptional points on it, but we don't know that. And for smaller values of L, so for example, for 11, X non-split of 11 has genus 1, rank 1. So you have to go to 11 squared. Same for 7 and 5. And for 3, it's even worse. X non-split of 9 is a P1. And so you have to go to 27. This one is close to or has been solved. There's a preprint coming soon from a group out of BU, so Jim Palagrishan and Ash, and a few others. And then there's just 2 that don't have a nice group theoretic description that are also problematic. So we'll talk about these in a bit. If there are any Heights people in the crowd, and I see a few, for this X non-split 11 squared has large genus, we can actually show, and I might have time to describe this, that if there is an exceptional point, the point has height 10 to the 10 to the 200. So you might think, I mean, that is very large. You might think that, great, maybe you can use some kind of method coming from Heights like Diamenchenko-Manin, but this unfortunately has no repeated isogeny factors in its Jacobian or anything like that. But still, that is large, and we didn't try that hard to get, we could get this number up much higher if we needed to. We have a roundabout technique. Yeah, that's a great point, Jordan. The logarithmic height is very good, 10 to the 200. Here's a table of the exceptional points. And again, if you go to the slides or our paper, this is all hyperlinked. And I'll just start at the top. This one was well known due to Heegner. X non-split of 16. So the normalizer of a non-split Cartan in Z mod 16, GL2 Z mod 16Z. This is a genus 2 hyperelliptic curve. Jacobian has rank 2. Heegner computed equations for this. And then you can check that there are actually 2 elliptic curves. Here are their J invariants, whose mod 16 image of Galois is contained, well, and their twists are contained in this group. These are not highlighted because when I made this slide, they weren't in the LMFDB, so I couldn't hyperlink it yet. Most of the rest are. There's some pretty interesting groups here. For example, this is Drew Sutherland's favorite J invariant, probably. This group comes up as, so there's a local to global problem solved by Katz, which is if an elliptic curve over Q has a torsion point mod P for every P, does it have a rational torsion point? Either yes, or it's isogynous to something which does. If you ask the same question about isogenies, if an elliptic curve has a isogeny mod every prime, does L-order isogeny mod every prime, does it have an L-order isogeny? The answer is yes, except for this single counterexample or a J invariant of counterexamples. And that happens if and only if the image of Galois is contained in this particular subgroup of the non-split Cartan, mod 7. A lot of these other exceptional points were already known. Mazur's classification of isogenies is not as minimalist as torsion, in the sense that for torsion, the genus of the modular curve completely explains whether there's exceptional torsion. For isogenies, even back when it was Ogg's conjecture, there were lots of known examples. This is not a very large chain variant of, say, curves with an 11 isogeny. But conjecturally, this is the complete list of L power exceptional points. And then one of David Zwina's recent papers has a conjecturally complete list in the composite non-prime power level case. So unsolved mysteries, these are the 6 curves from before. They're impish in the sense that in each case, the rank of every isogeny factor of the Jacobian is equal to its dimension. So you cannot do classical Chaboutier. They have rational CM points, but no rational cusps. But in particular, it's more difficult to show that a curve has no rational points if it actually has some. And these have no exceptional points. We've, to the extent we possibly can, checked on the modular curves using models, using other methods. Rank is equal to genus. So in principle, you could do non-abelian Chaboutier, and that's what Jinbi and Osh and others are doing here. They're not actually working on the genus 12 curve. Over a quadratic extension, this curve covers the genus 3 curve. So they're improving non-abelian Chaboutier. I mean, this is still incredible, to non-hyperelliptic genus 3 curves over a quadratic field to handle this case. But these others don't, even 9 is kind of large. They seem slightly hopeful that that's accessible, but 551 is not. And then I'll show some graphs later, but here's a table with the data. I'll just kind of stick to the case with 2. There are actually a lot of different subgroups that can occur as the 2-adic image of an elliptic curve over 2. There's lots of genus 1, rank 1, or genus 0 modular curves. 1208 is a much larger number than we expected. But of course, it trickles off and then conjecturally should stabilize. And then I need to remove some of these stars. So the stars are there because for 3, 5, 7, 11, actually 17 is known now too. This is only conjectural because of the unsolved mysteries. But if those are solved, we would know.
Dave, just before you barrel on, just a question from Jordan in the chat. Um, Whether you have a conceptual explanation for why the J invariants of the exceptional points are so often integral or close to integral?
Yeah, that's a great point. 2 reasons. Well, they are very rarely actually integral, but 2 reasons. One is these groups are very special. So if you often they have kind of high index, and so if you had a prime of multiplicative reduction, the Tate curve gives you a transvection, and that's often incompatible with whatever group is there. Not always, because you do see some of these, but then having 2 or 3 transvections is also pretty unlikely. Oh, that's a good question. So for Jordan's question, yeah, that's the answer, which is actually the group theory plus the like non-computational image of Galois type stuff you do, where if you have a prime of good but super singular reduction, the image of inertia looks like this. Like those kind of computations actually rule out a lot as well. And then David Corin asks, are there mysteries with smaller genus? Well, I mean, for example, the sexton split of 16 has rank equal to genus. But in this setup, these are the only 6 L power level up to 11 that we can't handle right now. So 17. Actually, this is an excellent question, David. So for 17, the remaining case was genus 6. Its isogeny factors had dimensions 1, 2, and 3. And then I think they are, I'm not certain, I think they are able to handle that case. So that actually would be kind of the next natural case. I'll say one other thing. A lot of the exceptional points that come up are very close to being Fermat triples. John Voight, I don't see him here, but made this observation to me and some of my students, but we haven't really followed up on that yet. And that there's a modular framework that this all fits into. Here's some applications. The only shade I ever have to throw at my good friend Jeremy is that when we started the original version of this project, just looking at 2-adic instead of all l-adic, he never told me his original motivation. And so we submitted a composidio and they wrote us back and said, "Oh, it's a good paper, but it'd be good if we had some motivation." And he was like, "Oh, well, I guess I could have put in my actual reason for studying this problem, which is arithmetic dynamics. It's a really concrete problem. Take a point of infinite order on an elliptic curve and ask how often is the reduction of that point odd order." Um, the answer, it turns out, depends on exactly what the 2-adic image of Galois is. Um, and surprisingly, generically, it's not half, it's like slightly more than half. It's 11 over 21. The largest it can be is 121 over 168. The smallest it could be is 1 over 28. And by the way, these don't exactly correlate to the size of the image of Galois. There's some adelic integral or p-adic integral that you have to do that computes this for you, that Jeremy and Rafe Jones had worked out in an earlier paper. Uh, so that's a pretty, I like that application. There's others though, which are more about torsion, classifying the possibilities for take an elliptic curve over Q, look at its torsion over the compositum of all cubic fields. And you can classify that completely. Uh, you can also classify when the image is abelian, but notice n is not prime here. And then one thing I'll talk about is both our main theorem and many of the techniques that come up in the proof of it give us improved algorithms for computing images of Galois. It's very fast these days. I'll say one other which didn't make this slide. Even I was surprised to find Jack Thorne used my original result with Jeremy to prove some version of modularity where they just needed to know x naught of 15 when you base change to a certain infinite extension what its torsion was. And so they used our theorem to help compute that. All right, let's talk about the proof. There is some enumeration. The graph will make the following slide more clear, but the way this works is when you start with x of 1, that has genus 0. Many of the modular curves covering it have genus 0, but you get kind of a tower of these where the genus grows, and eventually you get kind of a collection at the top, which all have higher genus or genus 1 rank 0, or generally you have a collection at the top which have finitely many rational points. Anything below it has infinitely many, and anything above it maps to one of these. So we define such subgroups to be arithmetically maximal if, well, a couple easy group theory conditions. So it needs to have surjective determinant, otherwise there are no rational points. It needs to, if you're over Q, respect how complex conjugation acts. So this is necessary for our points. And then we want the ones which are just barely finite. So they're finite, but any modular curve it maps to is infinite. And then by bullet point 3, every other modular curve with finitely many maps to one of these. So again, Sutherland and Zwina did the first big step, which is, excuse me, to compute for which subgroups you have infinitely many points. So the kind of penultimate in here. I'll start with 13 instead of 2 because you can actually read the labels. You'll see what I mean. And please stop me if this slide needs more clarification. So if we want to compute the 13-adic image of Galois, here's how the subgroup enumeration goes. There's GL2. Okay, every image is contained in GL2. But for the ovals, I'm thinking Z mod 13Z, so level 13. This has maximal subgroups. So Borel, split Cartan, non-split Cartan, and this exceptional one. Blue and Perrant and Robledo proved that the split and non-split, Balakrishnan and others using non-abelian Chebuti, this is a very computational paper that's in the Annals, proved that these particular curves have no rational or non-cuspidal non-CM rational points on them. They're genus 3 non-hyperelliptic, rank equal to genus. This S4, they also handled, this actually has some exceptional points. The Borel, on the other hand, has genus 0. So there are infinitely many elliptic curves with a 13 isogeny. over Q or any field. To move deeper or to higher index, we don't need to think about any other group whose reduction mod 13 is a subgroup of the split Cartan or non-split or S4 group, because if the image mod 13 is contained in a split Cartan, it would already give us a point on this modular curve. So this is why this graph kind of stops there. There are subgroups of split and non-split. It's just that they're no longer arithmetically maximal. On the other hand, this Borel has a bunch of subgroups. For example, star star 0 star, you could ask the upper left entry to be a perfect square. Or you could ask, anyway, there's lots of index 2 subgroups where you should think about it as you have an isogeny, but maybe the isogeny character is defined over a smaller field than it is generically. And lesser known fact, those index 2 subgroups, most of them have genus 0 as well. So there are infinitely many elliptic curves over Q with a rational 13 isogeny where the upper left entry is a square mod 13. But then you can intersect these. So you could say whatever these conditions are, so you get index 2, index 2, index 4, these all happen to be genus 2, so hyperelliptic curves, and the rank is less than 2. I think it's 0, but it might be 1, and you can find all the rational points on these provably. So you don't need to consider, so you do need to consider subgroups of the Borel, and you do need to consider subgroups of those subgroups, but then the stops, these blue ovals on the second to top line, are more or less cofinal. Any other group of level 13, so mod 13, is a subgroup of something on this slide. Then there's one extra bit of work. You also have to go from mod 13 to 13 squared. So you could have the Borel star star 0 star mod 13 squared. That surjects onto the Borel mod 13. That's a genus 8 curve. Heegner worked out equations for it and its automorphism group and found that it mapped to a genus 2 curve that I think was rank 0. So Heegner handled this. So this is generally what the layout and strategy looks like for these type of problems. And you can see that a lot of different type of work gets combined. One other comment is this type of casework was present even in Mazur's original work. So for, Mazur handled prime level, you still need to go to prime power, composite, non-prime power, and the proof relied on people like Ligozat and Heegner working out by hand some difficult sporadic cases like this, or exceptional cases. We have a bookkeeping section of our paper that keeps track of all of that work, but even in Mazur's isogenies paper, there's a lot sporadicity. So 13 is not so bad. How bad can it get? Here's the picture for 2. This is the first time I printed out a picture from one of my papers and put it on my wall. You can't read the labels. You can tell that they're colored corresponding to genus. At the top, this corresponds to GL2. These are maximal subgroups of maximal subgroups. And except for, you can't quite make out the color at the bottom, like these blues have higher genus and finitely many points. This is what we mean by cofinal. So it looks worse than it is. There's about 700 groups here. I say it looks worse because most of these are genus 0 or genus 1, rank 1. And the trick is to find how far down do you have to go, sometimes to level 32, to find the curves with finitely many rational points. So steps of the proof. First, compute that graph that we showed you. So the arithmetically maximal subgroups. Second, do all the sensible things people do. So first, look for local obstructions, compute the isogeny decompositions and analytic ranks of the factors. So I said usual, but we had to invent some new techniques to do this, which I'll explain. Once you have the isogeny decomposition, it points you at what to attempt. If all the factors have rank 0, that's much easier than if some or none have small rank. When appropriate, compute equations for the modular curve, and then often you also need equations for the J-map. There are numerous numerous situations where we can analyze the rational points on the curve without a model, but in many cases we need a model. And then once we have the models, throw the kitchen sink at the curve, try every technique coming from, rational points on varieties until one of them works. And I'm surprised how far we're able to get with that. And then one other kind of topper to this was all for minus the identity in the group. That makes it stacky no matter what, but you work with the course space. If minus the identity is not in the group, you actually get a universal curve, and it's helpful to have equations for those universal curves in the same way that it is for x1 of n. And so we have some techniques which are a little bit orthogonal to the rest of the paper for computing those equations. So to show you how bad it is, it's actually not that bad. For other prime powers, these are the groups with infinitely many points. We didn't put the whole picture into here. This one's a rank 1 elliptic curve. The rest of these are P1s. To understand, to prove things, you have to work with powers of 11. But for the final answer, you only have to look at level 11. And we get similar pictures for 3, so it's a little bit worse. 5, it's not really a great structure to that graph, but it's comprehensible. And 7. So the labels are what they are: level 7, index 24, genus 0, tiebreaker 3. But again, in the LMFDB, you can get your hands on these groups and really play with them a lot. So in the final 7 minutes, let's talk a bit about how we do each of these steps. So actually for the equations, the basic idea goes back at least to Galbraith, but probably older than that, which is, okay, the canonical map for a non-hyperelliptic curve given by differentials. Generally, this is an embedding. Generally, the relations are quadratic, and you know how many there are. For a modular curve, differentials are modular forms, or at least differentials with some controlled poles. So when computing equations of modular curves, you can exploit the fact that you know the power series expansions at infinity of the differentials to facilitate linear algebra. And so my go-to example that took me an hour to code up in Magma, which is not typical, and ran instantly is the following. X1 of 17 is genus 5, non-hyperelliptic, non-trigonal. So it's canonical embedding, lands in P4. It's the last such complete intersection. It's cut out by 3 quadratic equations. There are 5 cusp forms. And the way you should think about computing equations for this are, well, here are the equations, but how did I find these? I set up a general quadratic equation where the coefficients of each monomial were variables. And then I plug these 5 modular forms in to x, y, z, w, u, and then take as much precision as I need until the coefficients of these quadratics are determined, or rather determined, there's 3 equations, so you get a 2-dimensional vector space of them. So it really is, using some theory, but it really is linear algebra, at least in this naive way. So my original paper with Jeremy, part of the idea was, and I'm actually going to skip most of this, is Jeremy had some new ideas for how to efficiently compute equations of these modular curves. These have been improved and improved. So Iranisov and then David Zwina's recent papers really are the state of the art on this, even though our paper is not that old. And these techniques are, none of them exactly subsume the others. Some are better. But it really, in the end, goes back to this idea of using modular forms to facilitate linear algebra. Step 2, the kitchen sink step, is this is everything we had to do, but this is also kind of a complete list of the techniques you use and rational points on curves. The first box is what Jeremy and I did in our original paper. So we just, everything and everything else: Chabuti, elliptic, prim varieties, étale descent. We had a couple innovations. We figured out for these modular curves in some situations how to do étale descent without having the equations, without having just via group theory in some way. And actually a big help was Jeremy had a really good observation about faster ways to compute automorphism groups of curves. And in two sentences, in magma, if you just ask it for the automorphism group of a curve over Q, it might spin its wheels for a very long time. Over a finite field, it's very fast. On the other hand, you can write out effectively the Hilbert scheme of automorphism. You can write out the defining equations of the automorphism group, compute automorphisms mod a prime, and then Hensel lift them, or try to Hensel lift them to Q. Maybe they end up Hensel lifting to some number field where the prime splits. But if it's in Q, you can see this. And somehow this is much faster than just having magma compute it naively. And the reason you want automorphisms is if your curve is too big, take a quotient by an automorphism and see if you're lucky or not. In our current paper, in the last couple of minutes, I'll explain a few of these, but one of the big ideas is working without equations. And so computing, so Drew and David Zwina in an earlier paper, when x sub h is an elliptic curve, particular dimension 1, realize you can compute the number of FP points via moduli. So one good way to think about this is on x1 of n, you can compute that number without having the equations for x1 of n roughly by enumerating elliptic curves over FP and computing their n-torsion subgroups. So you have to be careful about extra automorphisms and cusps and so on. It's a lot more annoying than you might think. And as far as I know, this idea goes back to Ogg's paper where he classifies the hyperelliptic modular curves. He uses a similar point counting via moduli technique. Since I'm low on time, I won't go into Deligne-Rappaport, but you have to look very carefully at the moduli interpretation from x sub h. But once you do, you can, via enumeration, compute explicitly the number of FP points or the set of FP points without having the equations. And I've hyperlinked some slides of Drew that give a really nice summary of how this works in the implementation. And this is great because sometimes that number is 0. So we have a big list of curves with no FP points, in particular, no Q points that were somewhere in our list of modular curves. This doesn't happen a lot. They all fit on one slide, but it happened in several key situations. The other big improvement here is this actually gives us a way to compute the isogeny decomposition of the Jacobian of x of h. If you can point count enough, and if you have a bound on the set of modular forms that could occur, then point counting lets you, again, use linear algebra to interpolate what the isogeny decomposition is, and in fact, what the analytic rank is. So to do this, we needed two things. One is, again, we needed this point counting from before, but it was actually not known that the isogeny factors of these x sub h's were modular. What I really wanted to know was that the isogeny factors satisfied Kolyvagin's theorem. They were finite if and only if the analytic rank was 0. So in the appendix with John Voight, we proved that these are modular. In fact, we proved that each isogeny factor, if h has level n, comes from a form on this particular group. And then use that to explicitly compute the isogeny decompositions and analytic ranks. So there are a few other techniques. I've given other versions of this talk before if you want to see more about that. There's one other great thing where you can compute, you can do other usually very explicit techniques without equations like the Mordell-Evasive. But I will end my talk there. Thank you all for coming.